Okay, so good afternoon. Today's lecture, we will be talking about forces and circular motion. We will solve a couple of examples of a Newton's law and circular motion. So we will be showing you how to calculate the net force along the centripetal acceleration direction. And then we will be introducing the friction, the two types of friction that we mentioned earlier in our previous lectures, the static friction and the kinetic friction. Then in next lecture, we will be covering Newton's third law and recap of dynamics. So the centripetal force is a force, it's a net force that is caused by the centripetal acceleration induced on the object that is going in constant speed at a curved path that with a constant radius. So in order for us to calculate that net force, which is in the same direction of the centripetal acceleration, if you recall, we said the centripetal acceleration is always pointing toward the center of the circular path. So the force, the net force, causing the centripetal acceleration is also pointing in the same direction. Now, in order to calculate this force, which we're calling it Fc, we need to apply Newton's second law along the axis between the object and the center of the circular path. So if I do this, then I would be applying sigma F equals to MAC, where AC is the centripetal acceleration, and the positive direction that I am using here for my reference is always pointing toward the center of this circular path. And also recall that the magnitude of the centripetal acceleration is that speed squared divided by the radius. So it is proportional to the speed squared and inverse proportional to the radius of that circular path. So keep in mind that this net force that I'm calling centripetal force is not a force that is separate than the forces that you have seen. It is due to this acceleration. It causes some changes, and then there will be a net force. But the forces that you are calculating this centripetal force from are the same forces that you have seen before. Gravitational force, normal force, friction force. So in order to understand how to calculate that force, let's look at this example here. In this example, we have a child has tied a piece of wood of mass 0.47 kilogram to a string and is swinging it in a horizontal circle of radius 83 per second. So if you think about it, he's holding the string this way, causing it to rotate in a circular path in a horizontal plane. The constant speed is 3.83 meters per second. What is the tension in the string if it makes an angle of 29 above the horizontal? So we need to calculate the tension in the string. So let me draw the problem here, the diagram for this problem, and I will draw it from two angles. The first one, I will draw it from the top and then from the side, facing the child. So if I am to draw it from the top, what am I going to see is the following. This horizontal, this path in the horizontal plane, this is the radius. I have the velocity tangential. So this is top. From the side, this is the piece of wood. From the side, I can see the piece of wood here. I can see the hand of the child. So this is the hand. Child. This is the string. And this is the tension force. And this is the gravitational force. And I will put my coordinates right here on the object, such that if you think of the radius, so this is the center of the path, right? This is the radius. And the angle here, theta, is 29 degrees. So theta is 29 degrees. I have the mass, 0.47 kilograms. I have the radius, 83 centimeters, which is 0.83 meter. I have the speed, which is the magnitude of my velocity here, as 3.83 meter per second. So the first thing to do is to put the direction of your motion in the direction of the centripetal acceleration, which is pointing toward the center of the circular path. And that's what I did here for the X. The positive is pointing from the object toward the center of the circular path. And now I need to apply Newton's second law. Keep in mind that the acceleration here is in this direction. Okay? Now, let's apply Newton's second law, which is basically along the x-axis. So I have Fx equals to m times AC. So can you tell me what are the forces that I have along the x-axis? What do I have along the x-axis? I only have the component of the tension force on the x-axis. So having said that, I will draw this component, which is basically projecting this. So this one is Tx. So if I am to put the y-axis then this one would be Ty. So right now, I'm only interested in the x-axis because this is the direction that I have the centripetal acceleration. So sigma fx is indeed Tx, only Tx, equals to m times AC. What is Tx in terms of the tension force? T times cosine 29, right? So this is the Tx, this is the x component of the tension, which is basically T times cosine theta, which is 29 degrees, equals to AC is V squared over R. Is that right? Then in this case, T, the tension is M times V squared over R times cosine 29 degrees. Then if you substitute 0.47 times 3.83 squared divided by 0.83 times cosine 29 is 0.87. Then if you do the calculation, you will find that the tension force is 9.5 Newton. So it's 9.5 in Newton. This is the tension force. But which one is responsible for the centripetal acceleration? Tx. Tx is the net force in the direction of the centripetal acceleration. Any question about this example? Yes. This is the centripetal acceleration that we have introduced earlier. We said that the magnitude of the centripetal acceleration is V squared divided by R, where V is the constant speed along the circular path and R is the radius of that path. Any other questions? Okay, so now let's move on to the next example. In next example, we have a 1,000 kilogram car moving at a constant speed of 21 meters per second, crosses the rounded top of a hill that has a radius of 100 meters. So the car, as you can see, you have a rounded hill. He's crossing with a constant speed of 21 meters per second on that hill. We need to calculate the normal force exerted on the car. Exerted on the car by what? By whom? By the street. The street that this car is taking on this rounded top of a hill. And then we need to calculate the car's speed if the normal force is 0. So let me start first by drawing this rounded top that has a radius of 100 meters. So I have mass 1,000 kilograms. I have the radius as 100 meters. I have the speed as 21 meters per second. And I have, So if this is the car, then let me draw the coordinates. I'll draw the coordinates such that my positive axis is going from the object toward the center of the circular path. Straight enough? So let me call this one X. So just to make it more accurate. So let me take this one as X, this one as Y. So I have the gravitational force pointing downward. And I have the normal force pointing upward. In this case, the acceleration is pointing in this direction. The centripetal acceleration is pointing downward in this direction toward the center of the circular path. Now, if I apply Newton's second law, and I'll take sigma Fy equals to m times AC. Then if I substitute now where I have sigma Fy being Fg minus Fn equals to m times v squared over r. I need to calculate the normal force, so I'll take Fn to this side, bring mv squared over r to the other side. What do I get? I get Fg minus m times v squared over r equals to Fn, or Fn is Fg minus m v squared over r, or Fn is m times g minus m times v squared over r. Fn, take m outside, g minus v squared over r, or Fn is 1000 times 9.8 minus 21 squared divided by 100. If you do the calculation, you'll find that Fn is 21 squared divided by 5,390 Newton. So the normal force is 5,390 Newton. How much is the gravitational force? M times 9.8 9,800 Newton. So because of this centripetal acceleration and because of this centripetal force, the road that the car is taking on top of this rounded hill is now facing less force. See, what is the gravitational force? 9,800. The car gravitational force is 9,800 Newton. Because of this centripetal acceleration, now the road along this curved road, the road is putting back a normal force of 5,390 Newton. So the road is seeing relatively or putting less force than he would put if this car was going in a straight path. This is not far from what we have from the example that we evaluated a few lectures ago, the elevator. If you recall, in the elevator, if you were taking the elevator, accelerating up and putting the scale under you, you would see that when you accelerate up, the scale is going to read more than what you expect to see. However, if you take the elevator and accelerate downward, you will see yourself lighter. You're going to lose some weight. If you compare it with measuring your weight in a stationary position, right? So this is the same. Here, the acceleration, the centripetal acceleration, however, is the cause for that normal force to be less because of this centripetal acceleration that this car is facing. Is that clear? Any questions so far? No questions? Okay, so something to pay attention to and be careful of. This centripetal force is not a separate force of nature, like the gravitational force or the normal force. This centripetal force is due to the existence of the centripetal acceleration that's causing the net force to be non-zero along the direction of the curved toward the center of the curved path. Now let's look at this example. This is another example. In one of the examples we did, we were evaluating a circular motion going in a horizontal plane, right? Now it is different. Now we're looking at a motion that is going vertically. So it is as if you've held some kind of, weight with a string and you start swinging it this way, vertically. What's going to happen to the tension in the rope? So the question is asking the following. If we have this ball that is being swung on a rope in a vertical motion with a constant speed, where along the path is the tension in the rope is the greatest? Is it at the bottom or at the top? Right or left? Or the same everywhere? What do you think? Do you have an answer to this problem? Feel free to participate. Yes. Your colleague is saying bottom. Do you have a different answer? So 2 are saying bottom. Do you agree? Who has a different answer? Yes. Same everywhere, which is E. Okay. So the correct answer is B. But why B? So let's have a look and find out why B. What I'm going to do here, I'm going to solve for the top and the bottom. So this is the top. This is the bottom. Again, this is a vertical motion. So that's the center of my motion, of my circular motion. And here, this is the ball bottom, the ball top. This is the rope. That's the rope. Now let me put my coordinates right at the object, keeping in mind that the axis that goes to the center of my circular path is the direction of the positive. So if I am now to put this is X, this is Y. Notice that the positive direction is from the object toward the center of the circular path. Now, if I am to put it here, this is Y, this is X. So here, the acceleration is in this direction. Here, the acceleration is in this direction. Pointing toward the center, right? It's always pointing toward the center. Now, let me put the forces. Here, I have the gravitational force pointing downward. I have the tension force pointing up. Let me call this one TB, tension for the bottom. Here, the second one, I have the gravitational force pointing down as usual. And guess in what direction is the tension? The tension pointing down. So I will put here the tension force and I will call it TT, top. Now let's write Newton's second law for both of them. So I'm intentionally solving them simultaneously just to show you the differences, where to pay attention when you define the forces and what is the difference. Here, my centripetal acceleration is happening along the y-axis, so it's going to be sigma Fy equals to m AC, right? Sigma Fy, positive up, meaning TB is positive, minus Fg is negative, m times v squared over r. So TB is m times v squared over r plus Fg. Notice that the gravitational force does not change. The gravitational force is a function of the mass and the acceleration of the gravity. Let's look at the second one. Sigma Fy equals to m times AC. Both of them are positive, the tension and the gravitational force. So I have here Tt plus Fg equals to m times v squared over r, which is Tt as m times v squared over r minus Fg. Which one is a greater? TB or TT? TB, the bottom is greater than the top. Now let's look at the left and the right. Which one do you think? Do you think the left and the right are greater of both of them or less than both of them, or where? I'll do that very quick just to save some time. So I have the ball here to the right, here right. Here left. Now, not to forget the direction of the motion is going this way. So when you put the velocity, you make it tangential toward the motion. Keep this in mind. Right? So let me put the coordinates right here. So this is x. This is x positive from the object toward the center. The direction of the positive from the object toward the center. This is y. So I have the tension is this way. So this is TR. I have the gravitational force pointing down. Fg. Here, I have the tension from the object toward the center. T left, I have the gravitational force pointing down. Sigma Fx equals to m AC. The only force I have along the x-axis is TR. Sigma Fx equals to A times m times AC. The only force I have along the x-axis here is TL. So you can see that TL and TR are equal in magnitude and they fall in the middle. So I have here TB, then TR that equals to TL, T top. Right? Any question about this problem? Before we move on to the next one. Now we need to introduce the frictions. So we have, as I said, two types of a friction. We have the static and we have the kinetic. The static friction is when you have an object that is stationary. In this case, there will be a friction force opposing the force that you are putting. But once this object moves, then the friction force becomes kinetic friction force, which is basically less than the static. So those forces, the friction forces, are a function of the normal force, which is the force that's been put by the surface against the object. There's also a coefficient that is related. We call it the coefficient of static friction, μs, that is unitless. And we have also the coefficient of the kinetic friction, μk, also unitless. So when you calculate the frictions, it depends on those coefficients multiplied by the normal force. So if you want to calculate the friction, if you want to get the maximum friction, as we will see later on for the static, we have to use the normal force. So just an example, if you have a steel that is moving against a steel, there's a friction, you will notice that this coefficient is for the static, 0.74. That's greater than the coefficient for the kinetic, which means that the force you're putting at the beginning is higher than the force you're putting if this object is moving in motion. So we always have the coefficient of the static friction greater than the coefficient of the kinetic friction. Now, when it comes to evaluating an object, if this object can move or not, you have to calculate the maximum static friction. Because this tells you what is the threshold that you need to pass in terms of the forces in order to have this object moving. Otherwise, if the force you're putting against the maximum static friction force is less than that force, then the object's not gonna move. So this is your threshold toward having an object moving. Calculate the maximum static friction force and compare it with a force that you are applying, trying to move that object. So just keep in mind. So let's have a look at this example. This is going to explain to us how to evaluate an object that is stationary with a force applied on it with the existence of the static friction. So a man exerts a horizontal force of magnitude 512 Newton on a stationary refrigerator of mass 117 that is sitting on a horizontal floor. The coefficients of friction between the fridge and the floor are μs 0.69 and μk 0.6. Does the fridge move? Again, we said in order to know if the fridge moves or not, we need to evaluate the force that is applied against the maximum static friction. So to do this, let's draw the free body diagram for our problem here. So we have the fridge, gravitational force, normal force, and this is the force exerted by the man here, F. So we need to calculate the force the maximum force. Now this is the case if the object stays stationary. So let's first calculate the maximum static force applied by the floor on this fridge and evaluate it against the force that this man is putting to push the refrigerator. So in order to calculate the Fs max, which is mu s times Fn, I need to calculate the Fn. So to do so, I'll put my coordinates here. X, Y, and then I will apply Newton's first law because the motion along the y-axis, I have no motion along the y-axis. That's why I can apply Newton's first law, which is sigma Fy equals to 0. I have Fn positive minus Fg equals to 0, which means Fn equals to Fg, and this equals to m times g. So Fn equals to, the mass is 117 kilograms times 9.8. So Fn is 1,147 Newton. This is Fn. This is the normal force. Now let's calculate the maximum static friction force. Fs max is 0.69 times 1,147. Fs maximum is 791 Newton. This is the maximum static friction force. Now, if we evaluate the force that is being applied to push this refrigerator, how much is that force? So this is the net force that is applied against my friction, my static friction force. This force is 512 Newton. So since the net force along the x is F is less than Fs max, and this is also along the x axis, right? So the static friction is along the x-axis, and this F here applied by the man is also along the x-axis. So since this force is less than the maximum static friction force, the fridge will not move. So you look at this maximum static friction is your threshold that you have to exceed in order to have the object moving. So to understand this, any questions so far about how did we evaluate this example here and decided that this object or this fridge is not moving? Yes. Why did I apply Newton's law? I applied Newton's law along the y-axis because Newton's first law, because I have no motion along the y-axis. Right? Remember, if this fridge is to move, then it will be moving along the x-axis. The y-axis, there is no motion. That's why the acceleration along the y-axis is 0, and that's why we applied Newton's first law. But let's look at the second example, at this example that will make things clearer. We have a large box, mass 10 kilogram, is sitting on a horizontal floor. The coefficients of the frictions are μs 0.1 and μk 0.05. A horizontal force of magnitude 7 Newton is applied to the box, but the box does not move. Use G as 10 meter per second square for simplicity. While the 7 Newton force is being applied, the static frictional force acting on the box must have a magnitude of 10, 7, 5, or not enough information. So let me draw this. So here I have this box, mass of 10 kilograms. G, for simplicity, we're taking it as 10 meter per second square. Gravitational force, normal force, right? And then we have 7 Newton applied. We need to calculate the friction force, the static friction force. So if I am to put my coordinates here, x and y, and to apply Newton's first law, so I get here now Fn equals to Fg, 10 times 10, Fn is 100 Newton. Then in this case, Fn is 100 Newton. Then Fs maximum is 0.1, μs is 0.1 times 100. Fs maximum is 10 Newton. This is maximum. Now the question is asking, how much is the friction force, the static friction force? Is it 10, 7, 5, or not enough information? You know? 7. Why 7? Exactly. So the net force would be 0, and in this case, based on the Newton's first law, the friction force applied by the box would be 7 Newton, although the maximum is 10. But right now, because the box is not moving, it should be 7 Newton. So we will stop here.